Hi there, my name is Alex Shalaby, and today I'll be speaking about simulation of phased arrays behind electrically large platforms. So that's the agenda for today. I'll start by describing the problem at hand, the ways to solve it, a typical example, which is a Vivaldi antenna array at X band. Then there's two ways to solve that. The so-called full wave, which is the most accurate way, and then the asymptotic, which is less accurate but very fast, and then a decision flow chart to help our customers decide for their typical scenarios, and then finally, conclusion. I describe this problem from a computational point of view as really worst case. On one hand, we have an antenna array, and antenna array are very common nowadays. Just to name a few examples, 5G, MIMO, Wi-Fi routers, your smartphone, some medical devices, or even any multi-excitational electromagnetic device. And then these devices are never in isolation, otherwise they'll have no point. So they are always on a platform. This platform could be a radome for protection, environmental protection, could be a human body, it could be a ship. So you have a combination of something of multi-excitations, which is computationally expensive, and you have something electrically large. And when I speak of electrically large, I mean the physical size in meter, for example, or in millimeter, divided by the wavelengths. And electrically large is, we're speaking here, hundreds of lambdas, yeah? So, and that's not only for one frequency, but for multiple frequencies and multiple look angles. And otherwise, we would not need an antenna array. I mean, the first reason to use an antenna array in first place is to have multiple look angles. So as you see, it's really the worst case scenario from a computational electromagnetics point of view. There are several ways to tackle this problem. First is if you have enough resources, you'll do everything in finite element method, FEM. And that's the easiest way, but computationally most expensive. We call that full wave because that considers all the wave phenomena. So that's most accurate. There's another method, which is a combination of you put the antenna array in FEM, and then you do the platform and method of moments. That's also still full wave. Computationally, let's say less expensive, but just to set up the model is a bit more involved. Or last but not least, you do the antenna array in FEM. And it's always important to do the antenna array in FEM because this is where the electromagnetic field is created. Yeah, so you need the highest accuracy there. And then you can do the platform on SPR. On SPR, that's an asymptotic solver. It's the latest generation of asymptotic solver. Asymptotic solver started by geometrical optics, physical optics, and then ended with SPR, and now we have SPR plus. And these are very, very, very fast. Yeah, you'll see later. So that's an overview of the computational electromagnetics from HFSS point of view, but that's not only related, I mean, or limited to HFSS. I mean, most commercial products have more or less the same solvers. So on the x-axis, we have geometry and material complexity. So as you go on the x-axis, then material and geometry complexity increase. And on the y-axis, we have electrical size. So as you go on the y-axis, electrical size increase. And as explained before, electrical size is geometrical size divided by wavelength. So here usually is the electromagnetic field is created. So here you want the most accurate method. So you start by FEM. And if your electrical sizes increase, you go to integral equation or method of moment. That means the same thing. And using the latest variant of that, that's the fast method of moment, or MLFMM, multi-level fast method of moments. And if the electrical size is increased, you go to SPR plus. That stands for shooting and bouncing ray, and that really you can do very, very large problems. You can do even whole cities or and whole aircraft or ships. Then there is another technique, which is basically divide and conquer. You divide your big problem into smaller chunks, and you solve these chunks either on different cores on the same computer, or different cores on different computers connected through a technology called InfiniBand, which I personally highly recommend. So I'll go through briefly the pros and cons of every technique. I'll start with FEM because I'm doing this presentation from HFSS point of view. And FEM is the default solver in HFSS. The pros, it's good for inhomogeneous dielectrics with any shape and any intersection. So I said, regardless what complexity that is, that's no problem at all for FEM. It scales very well with additional hardware compared to mist of moments. So if you have 20 cores, you have a certain performance, and then you have 40 cores, then the performance doubles. So that really plays very well with the hardware because the matrix is sparse, whereas in mist of moments, the matrix is dense. And that's as a frequency domain solver with recent advancement from ANSYS, and credit due to them. If you have a multi-frequency or broadband, there's new techniques would make solving very efficient. Biggest disadvantage of FEM is air needs to be meshed. So if your problem have loads of air, that would be problematic. On the other hand, we have the mist of moments, or some people call it the integral equation, because it handles the integral equation formulation of Maxwell's equation. And if we, assuming also using the latest generation, which, as I said, it's multi-level fast mist of moment, the pros is air is not meshed, so that's the same structure I showed before. The cons is that it's a dense matrix. Yeah, so it scales with n cubed, and n is the number of mesh cells. So as you increase in size, it really gets more dense and dense, and that doesn't scale very well with the hardware. So you can't just send like through hardware on the problem and it will get better. Sometimes you get a saturation. On the other hand, we have the asymptotic solvers, which I said if you have a GPU, you have crazy speeds. So a problem which would take days on full wave would take minutes. It's very light in memory. You go from terabytes of memory to megabyte of memory. A plus means here, and that's only in HFSS, it can handle diffraction, so universal theory of diffraction and creeping wave. So that's better for curved objects. Hybridize with full wave. So for example, you can have the antenna full wave and your radome or your platform as SPR plus fully coupled, and it can has multiple bounces, which is more accurate for some scenarios, and it scales very well with frequencies. Or as you add more frequencies, just add minutes. Cone is it's not as accurate as full wave methods, and many people ask, okay, how accurate it is or how inaccurate it is, and actually that's the main goal of this, is to give you a typical example to answer that question. What are you compromising in accuracy in order to gain speed? And the short answer, not really that much. It's a tiny bit. So here, a typical example is a case study, Vivaldi antenna array in front of a dielectric radome. It's a staggered Vivaldi array so that you can fit it and you don't have diffraction loops. That's why we have a staggered 10 gigahertz. It's a very typical frequency for radar. It's explicit full wave, so there's no any approximation there. It's 81 excitation, and because as an antenna array, and that's the typical radiation pattern, if we change the coefficients, then it will have a different look angle. But the good news is for different look angles, you don't need to rerun the simulation. You just change the coefficients and you get the results, with, as I said, without rerunning the simulation. Now you can compromise on that and go from explicit network. I'm using the HFSS terminology. You can use composite. So composite is it valid only for one certain direction. You choose these coefficients before you start the simulation. And as we see, we go from 2 hours to 45 minutes, and we go from 183 gigabyte to 70 gigabyte. So we're saving a lot on time and resources. The only catch is it's valid only for one look direction, but it gives identical result. There's another ways to simulate the antenna array, which is beyond the scope of this presentation. I mean, this presentation is mainly about you have an antenna array, regardless how that was simulated. You want to simulate it. You want to simulate the platform, the influence of the platform. So one way is to do an explicit with Mesh Fusion. That's a brand new technology. I mean, highly recommended for certain scenarios. And a 3D component array decomposition, that's dedicated for antenna arrays, and for antenna arrays, it's very fast and efficient. So assuming that we already simulated the antenna array, we put it on a platform. So what are our options if we want to do it in full wave? As we see, there's variants of variants. So if we want to do full wave, we have two main categories. One is two-way coupled, which is RAM hungry, but gives you all look angles. Or the one-way coupled, which is RAM efficient compared to the two-way coupled, but has to be repeated for every look angle. So for the two-way coupled, and if you're lucky enough to have enough resources, you do FEM for both the antenna and the radome. You just put everything in one file and start. So that's the fastest, but needs more RAM. Or you can do Phoebe, which is finite element boundary integral for the array. So you put like a box around the antenna, and then do IE for the radome. It's slower than FEM for both, but use less RAM, and we'll see an example. Or you can do one-way coupled, which, as I said, has to be repeated for every look angle. So if you don't have many look angles, that's fine. If you have many look angles, that is not really worth it. So you have FEM for antenna array. You export the Huygens box, which is the near field source, and use this near field source to excite the radome in an integral equation fashion. So if we compare the two variants of the two-way coupled, they give identical results. That's the directivity, that's the radiation pattern. As we see, that's Phoebe plus integral equations, and FEM, it gives identical results in the peak directivity and the shape of the radiation pattern. One needs more memory, and so FEM for both array and radome, it has 5.5 million tetrahedrals versus Phoebe, which is Phoebe for the antenna array and integral equation for the radome is 0.7 million tetrahedral. So you see, yeah, it gives identical results. The difference is in RAM. So FEM for both needs more RAM because it has more tetrahedrals, but faster. The other one is slower, but needs less RAM. So see, the art is yeah, people say engineering is the art of trade-offs, and that's really the art here. Now let's compare, we're still full wave here, compare one-way coupled versus two-way coupled. So we have FEM for both the antenna and array versus FEM for the antenna array and IE for the radome. As we see, the characteristics is identical. There's a small shift, 0.2, we're speaking here 0.22 dB difference in peak directivity. So that's a very, very tiny bit. And we see we're saving, yeah. So if you're doing FEM for both, you would need 600 gigabyte RAM versus if you were doing FEM for the antenna array and then IE for the radome, for example, you would need here 40 gig. So it's 400 and then 40 for every look direction. See, you're saving RAM. So if you're limited on resources, that's not a bad idea at all. Now, let's say, okay, you don't have enough RAM, but you're lucky enough to have a GPU. And then you use an asymptotic, and as we say, the latest generation of asymptotic is SPR+. It started with geometrical optics, then went to physical optics, then SPR, then SPR+. As we see, the difference is 0.3 dB. It's not bad at all. It's not exactly the same shape, but you capture the main beam, you capture the first side lobes, and as you go away from the main beam, you have, I would say, slight differences. But you see, you're saving loads and loads of time. You're going from 28 minutes to 10 seconds. And you're going from gigabytes of RAM to megabytes of RAM. So that could be very good for initial designs, for example, or when you have a bid or you want to do an offer to your customer or you're under time pressure. That's a very, very valuable design tool. And as you said, it captures most of the picture. So just to summarize and give you a guide, I'm giving here this design chart, which should aid your design decision-making process. Is super speed important? If it's very important, then go for SPR+. There's nothing faster. Just bearing in mind that it's less accurate than full wave, but we're not miles away. Yeah, it's just tiny bit. Then if super speed is not very important, then do you have enough RAM? If you have enough RAM, then just go for FEM for array and radom. That's also the easiest from model setting, from setup point of view, and also the fastest. If you don't have enough RAM, then you have two options. If speed is still important, then you do one-way coupling. Yeah, so you do FEM for the array, and then you do radom mist of moments or integral equation. If speed is not very important, then you can do two-way coupling. Here, so you're using less RAM, but yeah, but it's slower. Yeah, so and that's all your trade-offs. Remember, SPR is slightly less accurate than full wave. As we've seen, we're not miles away. We're speaking, I mean, decimal places difference in dB. And one-way coupling is here, both if you're comparing full wave to full wave, I mean, one-way coupling, full wave to two-way coupling is slightly less accurate than two-way coupling. So two-way coupling is king in terms of accuracy, especially at the back direction, yeah, because that's the blockage from the antenna. So conclusion, nowadays, electrically large problems could readily be solved in a fast and accurate manner, given enough resources, without the need for optical approximation, which was done in the past, geometrical optics and physical optics. Choosing the right solver for the right application is really an art and needs some experience. And hopefully the presentation that I gave today will aid you in that process. HFSS stands for accuracy, speed, and adaptivity. It can adapt to your problem because it has different solvers. And CADFEM is there to help you. We're always there to help you with know-how and choosing the right solver, setting up the model, but also creating the computational resources, yeah, HPC, high performance computing. I hope you enjoyed the presentation today and that was helpful for your future projects.